Hello everyone! I think I got too excited in the last section. I said that we're going to next divide polynomials. Sorry, they kind of throw this extra section in here. They could have done this section earlier. Remember when we learned how to add and subtract polynomials? And we realized all it really is you're combining like terms. They could have thrown this section right after that. So I'm not sure why this section's later in the chapter, but whatever. This is all it's just more combining like terms or adding and subtracting polynomials. It's just now we're picturing polynomials that might have more than one variable. So for example, let's see this guy right here. You got, that's hard to see, let me highlight it. Like x cubed y squared, that's one term, two separate variables. The next term is minus 5x to the fourth y, two variables. And then 7x is its own term, even though it has no y. And 2/3 is the last term. So, so far the polynomials we've seen have only one variable. But it is possible to see a polynomial with more than one variable. Mostly in your math classes in the future, you won't see these very often, but once in a while you will. Here's another example. This one's really extreme. You notice you have 0.2 a squared b c to the fourth. That's one big old term. And it's all one term because all four of those things are multiplied together. The 0.2, the a, the b, the c. You're only done with one term when you see a plus or a minus. So notice now I see a plus. That means the next term starting 4ab. And I know that's the end of that term because here comes a subtraction sign. And then the last term is bc squared. That's kind of how you can, especially with a lot of variables, it's kind of hard to tell how many terms are in this thing. But just remember that the terms are separated by a plus and a plus or a minus. So that's why this guy has 3 terms. About the first one, let's try to guess. How many terms does this guy have, the yellow highlighted one? It would be 4 terms, right? Because there's a minus that separates 2 terms, another minus that gives me 3 terms, the plus gives me 4 terms. Here's 1, 2, 3, 4. Not that they're asking for that, but it's kind of good to know. And then you have one more example here just for fun. This is a little short guy. Just 5w squared minus 3z. So either of those terms, there's only 2 terms there, but either of them only have one variable. But I guess total the problem has 2 terms, 2 variables. Yeah, it has a w and a z. Even though they're not mixed up within the terms, it's still technically a polynomial in 2 variables. Alright. Let's do example 1. You don't really need any explanation behind example 1. We've seen this before. Although I think we've evaluated a polynomial a couple sections back. They said, okay, here's a polynomial, evaluate it for x equals blah. It's just this time the polynomial we're given is a polynomial in 2 variables. So there's an x and a y, which means if they want you to evaluate it, they better give you two values, one for x and one for y. So all you have to do is kind of probably what you would guess to do. I'm going to rewrite this guy, but where every x was, I'm going to put a 2. So there was an x at the beginning and there was an x at the end. This guy was being multiplied by y, and y is, they want us to evaluate it at -3. So my xy will become 2 times -3 because those are the values of x and y. And then minus 2 times y squared. Oops. You know what? This is getting kind of confusing. Let me just rewrite this guy. Sorry. So it's an x times a y. I'm going to replace both of those guys with the values they gave me, 2 and -3, and then minus 2y squared, but y will be replaced with -3, and then plus 3x to the fourth, y to the third. I'm going to replace the x and the y with the numbers they gave me. So maybe I'll focus on the x first. X equals 2. Where are all my x's here? There was an x here. That's a 2. This term did not have an x in it, so I don't need to put a 2 there. The last term had an x to the fourth, so I'm going to put a 2 to the fourth. And all the remaining blanks were y's, but my y value that I want is -3. So I'm going to go ahead and replace all of them with -3. And let's see if we can simplify all those terms there. So let's see, this first guy here, that one's pretty simple. It's just 2 times -3 makes -6. I can do that. The next term, though, I got to be careful. It's 2 times -3 squared. I cannot multiply 2 times 3 first. Remember, order of operations says you have to do exponent before you multiply. So I better do that first. I'll leave the -2 alone for now. -3 squared, that's -3 times -3, that's +9. So be careful there. And this one I got to do something similar. I see some exponents, I better take care of those. 2 to the 4th. Okay, that's 2 times 2 times 2 times 2. That's 16. And then negative 3 to the 3rd. That's negative 3 times negative 3, which is positive 9, times one more negative 3. That makes negative 27. Holy shamoly, that's going to be a big number there. Okay, let's see what we get there. I'm just going to kind of rewrite. I had a negative 6 to begin with. That was the first term. And now I'm going to see what the second term is. The second guy is the negative 2 times 9 here. That'll give me minus 18 or negative 18. And the last guy, ooh, that one I might have to be careful with. That's 3 times 16 times negative 27. Holy shamoly. I gotta multiply those together somehow. Maybe I'll just start off to the side. I'll start with the 16 times 3. Why not? That'll be 18, carry the 1. 3 times 1 is 3 plus 1 is 4. Okay, so the 3 times the 16 makes 48, but now I have to multiply that by 27. Holy moly. And I see it's a positive times a negative. That's going to be a negative, whatever I get. Alright, let's try this. 48 times 27. I'll start with the 8 times 7, that's 56, carry the 5. 7 times 4 is 28, plus 5 is 33. I have to bring a 0 down there. And now multiply the 2 times the 8, that'll be 16, carry the 1. 2 times 4 is 8, plus 1 is 9. There we go. So it'll be, if I add vertically, 6, 9, 12. So it looks like 1,296 is the last guy. And the last step is to just combine all these numbers. You have negative 6, negative 18, minus 1296. How about I combine these guys? Negative 6 minus 18 is negative 24. So now all I like to do is combine 24 and 1296. I think I'm going to go back over here. I had 1296 already. I'm just going to bring 24 in. Since it's a negative minus a negative, it'll just be a big negative. Whatever 1296 plus 24 is. So I'll add it off to the left here. 6 plus 4 is 10, carry the 1. 9 and 1 is 10, plus 2 is 12, carry the 1. 2 and 1 is 3. The 1 has no one to add with. So there he is, 1,320 negative. That's what we get. When we take this polynomial, replace the x's with 2 and the y's with negative 3. Oh, it's kind of tedious, huh? Oops, hello, sorry. Alright, so that's how you evaluate a polynomial. A lot of times it's very tedious and boring, but what are you going to do? Alright, so the next idea is, we've seen before, we had a lot of definitions of all the parts of a polynomial a couple sections back. Like, what's the degree of a term? Remember, before we only looked at polynomials with one variable. So we said, oh, if you look at a certain term of a polynomial, it's the highest power, or it's the power on that variable. But if you look at that last example we did, where is it? Like, what if I said, hey, this third term here, the 3x to the 4th y cubed, what's his degree? Oh, it's supposed to be the power on the variable, but there are two variables. Do you take the higher of the two or what? So this kind of tells you what you do to find the degree. The degree of a term in a polynomial with several variables, like the one I circled, 3x to the 4th y cubed, it's the sum of the exponents on the variables. So the degree of that guy up there, 3x to the 4th y cubed, you'd actually add those two powers. 4 plus 3 is 7, so his degree would actually be 7. Kind of interesting. Okay, and then if you want the degree of the entire polynomial, it's still the same as it was before. It's the largest degree among all those terms. So let's practice that on this example they give us here. Example 2. Let me erase all this junk here. What do we have? Okay, we have 3 terms here. Because remember, one term starts and it only ends when you see a plus or minus. Another term starts and only ends when you see a plus or minus. And then the last guy. Okay, let's see the degrees of each term. This guy's degree. Remember, you're supposed to add the powers. I see. Be careful though, because there's 3 variables there. A has a second power, B has an invisible 1 power, and C has a 4th power. You have to add those together. It's 2 plus 1 plus 4 makes 7, right? Aha, so that term right there, the first term's degree is 7. Because you're adding all the exponents. A's exponent is 2, plus B's exponent is 1, that makes 3, plus C's exponent is 4, which makes 7. Now let's look at the next guy. It's 4AB. The exponents on the variables are 1 and 1, even though they're invisible. So 1 plus 1 is the degree of the second guy, that's 2. Alright, so the first term's degree is 7, the second term's degree is 2. The last guy, let's see. b is the variable. It has an invisible exponent of 1, plus you add the degree, or the exponent on c, which is 2. That must be the degree of that third term, 3. Alright, so kind of confusing, but yeah, if you have a term in your polynomial with more than one variable, just take every exponent on a variable, even if it doesn't have a visible exponent, it's still a 1, and you add them all together. That's the degree of the entire polynomial. We have each of the individual terms' degrees, but they also want the polynomial's degree. But like it says in that box, it says, the degree of a polynomial, it's still the largest degree. So all I have to do is look at the 3 numbers that I found. I had 7, 2, and 3. The largest of those was 7. And that's it. So finding the individual terms' degrees helps you to find the overall polynomial's degree. Because you just take the largest of the terms, or of the degrees. Alright, so hopefully that makes sense so far. It's kind of a lot to take in so far, but the rest of the section is pretty simple. It's just combining like terms. So of course combining like terms is more complicated if you have multiple variables in each term, right? But still, so I would think like terms, okay, before like terms we said, if you only have one variable, you can only combine terms that have the same exponent. But like if you look at example 3 part A, look at the first couple terms there. You have 6u squared v, 9uv squared. You think, well look, they have the same exponents, like there's a square and a square, and then a 1 and a 1, because kind of like this guy has a 1 power, and this guy has a 1 power. But you notice the exponents are on the wrong things. The first term has a second power on the u, and a 1 power on the v. But the second term is the opposite. It has a 1 power on the u, and a second power on the v. So these guys are technically not like terms. Like terms have to have the exact same powers on the exact same variables. So they're very picky about it. The same powers on the same variables. Yeah, so it's not enough to have the same powers somewhere. They have to be on the same variables. That's why the first 2 terms in this part A of example 3 are not like terms. So I've kind of have it misleading looking. It looks like I color-coded them in red, but no. So they're not like terms. Let me see. The first term, 6u squared v. I'm going to look and see if there's any other terms in this polynomial that are like to that. So what I'm looking for is there a u that's squared and a v that's to the 1 power? I actually see that here in the third term. Even though they're switched around, it's still v has a 1 power and u has a second power. So if you want, you can actually rewrite that guy. That's 3u squared v. It doesn't have to stay in that order. When you're multiplying 3 things together, it doesn't really matter what order they're in. So those will be like terms. I've got a 6u squared v, a 3u squared v. You'll add those together. 6 plus 3 is 9. And you keep the powers the same like before, u squared v. So we got those 2 covered. What about the second term? Does he have a like term? I have to make sure I see a 1 power on the u and a second power on the v. And I think I see that here in the fourth term. Even though they're switched around, I can write it as 2u and then v squared. Then I realize those are like terms, a u and a v squared. So I'll combine their coefficients. I have a negative 9 here, a negative 2 here. Negative 9 minus 2 is negative 11. And I'll keep their variables the same, u squared v. Alright, so I think we've used all the terms except the very last guy. And I think he's the odd man out. He's the only one that has a u squared but no v. He has no like term because he's the only guy with no v. With no v. So not only do you have to have the same exponents, you have to have the same variables. So if you're missing a variable that you see in the other terms, you're not a like term. Since he doesn't have a like term, he'll just stay the way he is. And in these problems, you know, it's kind of hard to tell. I don't know, it's not like you're going to really write it from largest exponent to smallest exponent. And I don't even think, there's not really a right order or a wrong order to put your terms in on these, since there's multiple variables. You couldn't even really go by degree, you know? If you think about, well, let me see which term has the highest degree. Look at the first term that we have in our answer there. What's the degree of that guy? It's u squared v to the 1 power. The degree of that, if you add the powers, 2 plus 1 is 3. But the second term has the exact same degree because it has a 1 power on the u plus the second power on the v. So the first and the second term are not like terms, but they have the same degree. So we'd say, wait, which one should go first? The whole thing about descending powers goes out the window, and you don't need to worry about it when you have multiple variables. So keep that in mind, yeah, if there are multiple variables, like we have. Pull multiple variables. Order of terms doesn't matter because it doesn't make sense to say the largest degree to the smallest degree, because you could have two of the same degree that aren't like terms. Doesn't matter. Yeah, we only care if say there's only one variable, then it is possible to put it in a certain order, and we probably should. But these guys, it's too complicated and too silly. Not worth our time to put them in a certain order. Alright, let's look at part B here. What do we have? What I do is, since it doesn't matter what order they're in, I just look from left to right. Look at the first guy, and then look at the rest of the terms and see if there's any one that's a like term with that. If there was another one that's a like term, it would have to have an a squared, a b, and a c to the fourth. And I do see a couple terms down here. That's a squared, b, and a c to the fourth. But those are the only two that have that, those variables. So they're like terms, they can be combined. And I know whatever I get, it's going to be some coefficient, and the variables will stay exactly the same. So those I can just write out right now. I just have to think about the coefficient. So I'd be adding or subtracting their current coefficients. It's a 0.2, I guess, minus a 1. Think of this guy as minus 1 a squared b c to the fourth. So I have to think, what's 0.2 minus 1? Well, 0.2 minus 1 is negative 0.8. That's kind of a tricky one when there's a decimal, huh? But yeah, 0.2 subtract 1 would be negative 0.8. We've got those taken care of. Now I'm looking at the next term. I've already taken care of those guys. Now let's move on. 4ab. Does he have a like term? If I scan the rest of the terms, I do see that the very last guy has an a and a b. Exactly the same variables, exactly the same powers. So those can combine. You have a 4ab minus ab. That's 3ab. Oops. There we go. So those two are taken care of. Now I'll move on. What's the next term I see from left to right? Minus bc squared. I do see another term that has a bc squared here. So I'll combine those. Negative bc squared minus 5bc squared. That's like taking negative 1 and subtracting 5. Negative 1 minus 5 is negative 6. And then same exact variables, bc squared. So those guys are gone. There's only one term left, and I think he was the only one that didn't have a like term, huh? 9a. So you can't really combine him with anything. There were no other terms that only had an a and no b. So that's it. And again, don't worry about, are these in the right order? Should I have this term before that one? It doesn't matter in these. It's just too complicated to say, oh, let's put them in this certain order. Anyway, yeah, like we saw in the last one, it's because there could be two terms with the same degree, and you wouldn't be able to decide which one should go first. Alright, let's do more of that, but this time, instead of just having kind of a bunch of random terms separated, maybe they're like terms, maybe they're not, we're doing a very similar thing, but we're thinking of, what if you have one polynomial here, another polynomial here? Think of them as two different polynomials, but since you're adding them together, just think of it as combining like terms. So that one, you can really just remove the parentheses. There's a plus sign in front of these parentheses, but you know, if you distribute a plus, that's not going to do anything. So like we've seen before in the section where we added polynomials, this is very similar. I'm just going to rewrite this guy with no parentheses. I'll just have to keep in mind for part B of this problem, notice there's a minus sign, so I'll have to be careful to distribute that negative or minus sign inside the second parentheses. But that's a problem for later. I'm not going to worry about that now. So now part A, now that I've removed the parentheses, this is a problem just like we saw in example 3. So now I'll just look from left to right, because again, it doesn't matter what order your terms are in. The first term I see is 2x squared. Now I have to look for another term that has an x squared. Okay, kind of down toward the end I see another x squared. But those are the only guys that have an x squared. So 2x squared minus x squared, that'll make 1x squared, or just x squared. The next term I see from left to right, a negative 3xy. Do I see any more that have an xy? Well, the last guy kind of looks different, but it's yx. But remember, if three things are being multiplied like that, 5yx, you're free to switch either of them if you want. So that one, it really is the same thing as 5xy. So those are like terms, because you're free to change the variables around if you want. So I'm taking negative 3xy, subtracting 5xy, that'll be negative 8xy. There we go. Now I'm kind of getting confused. Let me cross out all the things I've added so far. There's only two terms left, the two middle ones, and they're actually like terms, huh? They're both y squareds. So I have a 1y squared and a 4y squared, that makes 5y squared. I think that's a good looking answer. Again, don't worry about the order they're in, just Like, so let's say I wrote this answer and someone else, for some reason, they have, I don't know, 5y squared, and then plus x squared, and then minus 8y. Sorry, xy. That's a fine answer too, because notice that has the same terms as we have in our answer. They're just in a different order. Because order doesn't matter, these two answers are just the same, equivalent. I wouldn't say one's better than the other, just kind of how you happen to add them, what order you added them in. So yeah, I don't feel like you have to have them in a certain order, or if you're doing problems and you look at your friends and say, oh, that's not what I got, mine are in a different order. In this section, it doesn't matter, so don't worry about it too much. Alright, let's try part B. But like we said, I can just remove parentheses. I just have to be careful. Since I'm subtracting, I better distribute this subtraction sign onto every one in the second parentheses. And then I'll be able to kind of just remove parentheses like it's no big deal. The first parentheses, though, they're not really there for any reason. I'm just going to remove them and not worry about it. Just rewriting it exactly the same as it was. Alright, but then the minus sign in front of the second parentheses, I better be careful. That'll make that 7r squared t negative. It'll make the rt negative. And it'll make the thing that was already negative, the 5rt cubed, a positive. Because a negative and a negative make a positive. Alright, looks good so far. I think. Let me erase this crap here. I mean, stuff. Sorry. And, let me see. From left to right, I'm going to look at this guy. 2r squared t. Do I see any other r squared t's? Yeah, a little ways down. Here's one. Those guys can combine. I've got 2r squared t minus 7r squared t. 2 minus 7 is negative 5r squared t. Alright, and I think those are the only... If there was a third term that was the same, I'd combine all three of them. But I only see those guys. I think they're the only ones that are like terms there. Okay, from left to right, the next guy, negative 5rt. Do I see another rt? Yeah, toward the end there a little bit. There's a negative rt. So I've got negative 5rt minus rt. That's like negative 5 minus 1, so negative 6rt. Alright, I think there are only two terms left, right? We've taken care of these guys. They happen to be like terms. You have an rt cubed and a 5rt cubed. They have the same variables and the same exponents. So I'll combine them by saying, think of this as a 1 plus a 5, that's 6rt cubed. And that looks good. You could, if you wanted to, move those terms around if you wanted to, but there's not really any need to. You're just kind of spending a lot of time making it look different, but there's no need. But if you check your answer with someone else, or you check your answer in the back of the book, and you say, oh, I think I got the same answer, but look at theirs has, I don't know, the last term first, and then the middle term, like they've put them backwards. Does that mean I'm wrong? Now just remember that it doesn't matter what order these guys are in, it's the same answer, just looks a little different, that's all. So don't worry too much about it. Alright, the last problem here is an application. It's kind of hard to imagine where you would use these in real life, right? It's mostly, excuse me, where you'd use these in real life. Sometimes there's, I guess, a real life formula for something. If you're trying to calculate some quantity in geometry or in physics or some kind of application class, sometimes there are formulas that represent things, like this guy is what we'll be dealing with. It's a formula that has more than one variable in it. So that's, you can think of that as a polynomial kind of, because it has powers, it has variables, it has coefficients. But it represents something in real life. So let's see. This example says, a silo is a structure that is shaped like a right circular cylinder. So if you're curious right there, what is a circular cylinder? Picture like a soup can or a soda can, you know? It's kind of got a round shape, but it's kind of straight along the sides. So it's almost like someone took a circle and a rectangle and snapped them together, you know? Or something like that. So it's a right circular cylinder, but it has a half sphere on the top. So it's not only that, it's like a soup can, but someone put a half sphere on the top of it. So it's kind of, I don't know, what has that shape, huh? Other than a silo. Trying to picture it. So it's like, the top portion I drew shouldn't really even be there. It's like, more like this. Oh, like a bullet. That's what it looks like. Is that kind of a weird thing to say? Whatever. So it's got like the cross section. If you were to cut this thing, you know, chop it down, it would have cross sections that are circles, but the top of it is rounded. The bottom of it's kind of like squared off, you know? I don't know if you could picture that. But yeah, just kind of picture a bullet. You've seen a bullet before. It's got, the front of it's kind of rounded like a sphere, but the back of it's flat. So that's kind of how this guy is. There's a flat bottom and a rounded top. So this is kind of a rounded guy right here. It's all roundy. Anyway, nobody cares, right? Nobody cares what this looks like. They just want to finish this dumb problem. Just kidding. It's okay. If you've been curious, what's the surface area of a shape like that, right? You've probably wondered that all your life. That's been something that's kept you up at night. What is the surface area? And so surface area, that's just the measure of the outside. So I guess, what if this thing was hollow? Like, what if this was like a soup can? You know, soup cans or soda cans, there's no inside. It's not like a solid object. It's hollow inside. So if you want to measure, like, how much material was made, you know, how much aluminum did you use for the soda can or something? That's just the outer part. A measure of how much material was used, not the inner part, like the soup that's filling it. Not that, just the outer part. So that's really what surface area means. Like, or like if you had a balloon. That's not the shape that we're using, but imagine a balloon. That's kind of like a sphere. If you want to know, oh, how much, I guess balloons are made of rubber, right? I think. Whatever. How much rubber was used. You're not really measuring inside the balloon because the inside's filled with air. You're really measuring the outside, kind of like, so that's really what surface area means. A measure of how much material kind of was put into this, the outer part, not the inner part. Anyway, kind of interesting. If you ever have to take physics, you'll see surface area again, and calculus, you'll see it a lot. Anyway, okay, so they're saying, for this particular shape that's like a kind of a bullet shape, it looks like a soda can with a half sphere on the top, the surface area is 2 pi RH plus pi r squared. Okay, where r, I guess you can imagine what r stands for. When you're talking about a circle or a sphere, the r is the radius. So if you look at this picture, like here, from the distance from the very center of it to the outside, that's your radius there. And then h means you're talking about the height. Let's see, height would be from here to here. There we go. Yeah, it looks good. Okay. So they're saying that's what the surface area is. And specifically, let's say we have a grain silo. So there's a silo on a farm or a ranch somewhere. It's 20 feet tall because it has a height of 20 feet. So let's say ours has 20-foot height, and the radius is 4.5 feet. Okay, that sounds good. Let's find the surface area of the silo. So really, this is just an excuse for us to take this polynomial here, which looks complicated, and really what we're doing is evaluating it. Like the very first example we did at, what was the radius they gave us? 4.5 feet, and height was 20 feet. So it's really like, yeah, that first example we had, we just substituted x equals blah, y equals blah. We're going to do that here. It's just, I guess this is more like real life stuff. And also keep in mind pi. Remember pi, it's just the number 3.14. It goes on and on and on. So that's just representing some number. And I think in this one our answer, we'll just leave it with a pi. We're not going to substitute 3.14 in for pi. So I'm leaving here 2 and pi are just numbers. I'm not going to replace them. But the r and the h, I'm going to replace them with the values I was given. And then plus pi times r squared. R was given too. So I'm going to go ahead and replace that guy. So let's see, r was 4.5. There was an r here. See how that goes. There was an r here, 4.5. Alright, that looks good. And then h, they said the height was 20. So where the h was, there's only one h in this formula, but I'm going to replace it with 20. And we'll try to simplify this as much as we can. We'll see what we can do here. Alright, so I have a 2 pi here first, times 4.5. Okay, you can't, that's a mixed number, right? You can't really multiply a mixed number by whole numbers. So I think what I'm going to have to do is convert 4.5, which is a mixed number, to an improper fraction. Because improper fractions are better for actually doing calculations with. And this might be a good review. It might have been a while since you've done that. 4.5, okay, what you do is you multiply the 4 times the 2, so the denominator times the whole number. 4 times 2 is 8, and then you add the numerator. 4 times 2 is 8, plus 1 is 9, and you keep the denominator the same. So that's, using 9 over 2 instead of 4.5 is going to be way easier. So I think in both of these places, I'm going to replace the 4.5 with a 9 over 2. That's going to make these calculations way easier. And then I still got a 20 here, still got a pi here, oops, pi, and I still got a square here. Alright, let's see what we can do here. Well, in this is one big term here. I'm multiplying a bunch of stuff together. 2 times pi times 9 halves times 20. In order to multiply, these are like whole numbers times fractions. I better put these whole numbers over 1 and then try to multiply across. Although actually there's a little reducing you can do, because this 2 denominator, actually it could go into this 2, or it can go into this 20. It's up to you. I think it's easiest for it to go into 2. They just cancel. 2 and 2 cancel all together. So now all you're left with is the pi times the 9 times the 20. So 9 times 20 is 180, and then you have multiplied by pi, but I'm just going to leave pi as is. Alright, so that's this entire first term. That looks pretty good. The next guy, though, I'm going to have to think about this. Pi, 9 halves squared. Actually, we have this exponent rule that if you have a fraction to a power, you can distribute the power. Because you can distribute a power over a division, and you can think of this as like a division, 9 divided by 2. So that's becoming 9 squared. So I'm going to go, you can actually do that in your head if you want, 9 squared and write that out, 2 squared and write that out. But just to show kind of my work, I'm going to write out all these steps here. And this guy's waiting to see what happens to his friend over here. 180 pi is waiting to see what happens to pi times. That would become 9 squared is 81, 2 squared is 4. Alright, and then really you just do, we're doing 81 over 4 times pi. There's not much you can do with that, but maybe usually you see the number in front of kind of the symbol or the variable. Kind of like we saw with 180 pi, we wrote the pi on the right side. And even though pi is a number, you can kind of treat it like a variable. These guys are like terms because they both have a pi attached to them. So I might be able to add them, although in order to combine, I must combine their coefficients. Combine. So this is kind of almost like, what if you had 180x instead of a pi, plus 81 over 4x. Those would be like terms. You'd have to add, what's 180 plus 81 over 4? Anyway, so this one is kind of similar. It's just gonna add 180 and 81 over 4. That might be something you want to think about over here. What's 180 plus 81 over 4? Well, I can't add a whole number and a fraction, so I have to put the 180 over 1. And in order to add these, I'll have to have a common denominator. The common denominator will be 4, so I'm going to multiply the first guy by 4 over 4. He'll become, let's see, what's 180 times 4? 720. Ugh. 720 over 4 plus 81 over 4. That'll be, I think, 801 over 4. Is that true? Because 80 plus 20 is 100. Yeah, okay. So there he is. That'll be what we get when we combine these guys. 180 plus 81 over 4 is 801 over 4. But they have a pi attached, so there it is. 801 over 4 pi. And probably in real life, if you really cared about what the surface area was, you'd probably make that a decimal. You know, you'd use a calculator, say what's pi, multiply that by 801 over 4, and get some kind of, I don't know, get some decimal answer. That would probably be more useful. But in math, we like to keep it, look, this looks really pretty. This is not a decimal answer, this is an exact answer. So if you want to write this in words, you can say the surface area of the silo is this value we found, and the measurement that they were using is feet, so that must be in feet. Actually, it would be in square feet, sorry. Because if you're talking about area, that's square feet. Like, you know, people talk about how much, or how many square footage, or what square footage is your house. So it's kind of like that, since it's area. There we go, that's probably how we'd say it. So that's kind of an interesting example of where you could use this in real life. It's kind of overly complicated. I wouldn't put a problem that complicated on an exam. It's just, I think if you can follow along with that, then you know what you're doing. You're doing pretty good. Alright, well, thanks for listening, and I've been having a good time. Hopefully you have too, or at least not the worst time in the world. But we'll see you in the next section, and in the next section, I promise, this is actually going to be dividing polynomials, like we've been getting all excited about. So alright, thanks for listening. I'll see you in the next section.